You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
Chris, good morning. I've always wanted to know, so do you sit naked when you're taking this call? What do you do?
Just struggling out of my clothes right now.
Well...
No, for the sanity of listeners, it's the science that's naked.
Okay, so you're not buck naked. Okay, I'm glad. Tell us about this gene screen for heart disease. What's that about?
Well, scientists are trying to grapple with the problem of heart disease because heart attacks and diseases like strokes, which are disorders of the blood vessels, are the number one cause of death in the majority of countries in the world. Mm-hmm. And given that high risk profile, why is that happening in the modern world, and what can we do to prevent it? Well, we've identified a number of things that people do which make them at higher risk of having a heart attack. There's things like having diabetes, there's having high blood pressure, there's having high cholesterol, there's having a family history, poor lifestyle factors, low exercise. But there are also some important genetic triggers. And the present way we size up someone's risk of having a heart attack does not consider what lies in their genes at all.
Right.
And that means that we don't tend to be in a position to diagnose someone as at risk of a heart attack until they've got some of these other features and signs, which means by then their disease may actually be quite well advanced. So what a group of researchers internationally have done, and they're publishing in the European Heart Journal this week, is that they have taken a lot of the information that has surfaced in recent years about the genes which we know are linked to having heart disease, and they have taken 49,000 genetic markers called single nucleotide polymorphisms. These are inherited changes in the DNA, which what you do is you look at a very large group of people who have a condition, a large group of people who don't have a condition, and you see if any of these markers keep repeatedly cropping up in the people who do have the condition compared to those who don't. That means you can then go to someone at random in the population, you can tot up how many of these markers they have, and then you can, in theory, compute a score for their genetic risk of having that condition. They've done that for this problem with heart disease, and they have come up with a gene screen. They've got this score that they can apply based on looking for patterns of these markers in an average member of society. And it's a very powerful predictor of who is at risk of heart disease. And because your genes, you are endowed with your genetic makeup the minute you are conceived, this means potentially you could diagnose someone as having a high risk of heart disease from the minute they're born. And this means you could intervene much earlier in their life before their disease course even begins, and use drugs like statins, for example, aggressive management of blood pressure, and significantly reduce, they're saying, their risk of having a heart attack, which is very good news.
It's very good news. I'm thinking that you could start tailoring your lifestyle to make sure that you don't have the problem further on. And if it can be screened at birth or when you're still young, then the things that you have to do aren't too difficult because you don't need to unlearn them.
Well, that's true. We all learn bad habits, don't we? But as they also say, prevention is much better than cure. So if you get in early and stop the problem happening in the first place, then it's much easier to fix something that isn't broken yet compared to trying to unpick a whole tangled web of problems and sort them out.
We're talking to Dr. Chris Smith, the Naked Scientist. You can call us on 021 446 0567. Whether you're in Johannesburg or Cape Town, 021 446 0567. SMS us on 31702 or 31567. Get ready with your science questions. Now, let me ask you, Chris, how far is this genetic screen from being widely available?
Well, I asked Nilesh Samani, he's Professor Sir Nilesh Samani. He's from the University of Leicester. He's a cardiology doctor there. He's also the medical director of the British Heart Foundation and one of the authors of this study. He spoke to me a couple of days ago, and he said, well, I don't want to give the public too much hope that this is going to be on offer in the clinic tomorrow. But they're thinking they've got to go through and validate this, because at the moment they've looked at 15,000 people and their genetic makeup and tied from those people these markers to their genetic risk of heart disease. What they now want to do is to make sure this is appropriate for all sexes and all societies. So they're going to widen the screen, look at more people around the world, and then also check that question of if we do intervene early in these people, can we change the course of their disease? Because the paper can't explicitly do that. The paper can only say that we can identify who these people are. So those are their goals. It's probably going to be another decade before we're in a position to do a test on someone to say, right, okay, here is your heart disease risk at birth for later in your life, and this is what we need to do to make sure that you have 10 years of extra good health or 20 years of extra good health before this becomes a problem, compared with if you just go business as usual.
Okay, thank you, Chris. We're talking to Chris Smith, the Naked Scientist. If you want to call us, 021-446-0567 or SMS 31567 or 31702.
702 and Cape Talk.
The Naked Scientist.
Welcome back. You're listening to the Riti Hlabi Show on 702 and Cape Talk. My name is Songezo Zibi and I'm the Friday stand-in. I'm joined by Chris Smith, a Naked Scientist. If you want to talk to us, call us on 021-446-0567, SMS 31702 and 31567. For those who are used to calling 011-883-0702 in Gauteng and surrounding areas, that line is not working. There's some gremlins in the system. Please call 021-446-0567. Let's go to the first question. We've got Jimmy in Cape Town. What's on your mind?
Hi, Songezo. Hi, Chris.
Hi.
Hi, Jimmy.
Hi. My question is, what are the possibilities that the planet Earth could be the living creature? I'll listen on the radio. Thank you.
Is planet Earth a living creature? Well, I think this is really the idea of the Gaia hypothesis, wasn't it? The idea that the planet is itself an entity. Well, it depends really on how you define living, isn't it? We know that the Earth has components of it which are not alive. They are the same atoms and particles that the Sun is made of, other planets are made of, and they're found all over the universe. But unique assemblages of those atoms and molecules make living things. They make genetic codes that can be inherited from one to another. They make us. The planet itself isn't alive, but the system that flourishes and thrives around the planet and supported by the planet and nurtured by the energy coming in from the sun, that's very much alive. And as far as we can tell, we're the only example of it in our solar system at the moment. We might be the only example of it in the universe, although that seems unlikely. But what it does tell us is that it's a rare thing, it's a beautiful thing, and we should preserve it and watch out for it.
You know, the idea that it's very science fiction movie to me, that the idea that I could be a speck on a large living organism that can shed me any moment. We're taking your calls on 021-446-0567 or SMS 31702 and 31567. Let's talk to James in Cape Town. What's your question for Chris?
Yeah, hi, good morning. Morning all.
Hi, James.
My question is related to the naming of medicines and drugs. Being a father of three boys, I've come across a lot of medicines lately, being winter. And I came across medicines like Phlegm Ease, which is a cough mixture, and it pretty much speaks to itself. It eases the phlegm in your chest. And then you get drugs like Miprodol, which is a painkiller, and you take it and your pain goes away. My question is, how do the pharmaceutical companies name these drugs? Is it at random? Is it got to do with the chemical compositions? Or is it a pre-thought process rather than randomly?
It's all of the above is the answer, and it's also quite complicated. Now, confusingly, drugs actually have two names. There's the pharmacological name, which is the name given to the molecule that makes the drug work. And then there's the trade name, which it's marketed under. So, for instance, if we take aspirin as an example, aspirin actually was the first example. Bayer Pharmaceuticals made aspirin in the early 1900s. And that was the first example of a drug that was made as a trade name because they discovered they couldn't patent the molecule because someone had already invented it. The molecule that we call aspirin is actually acetyl salicylic acid, ASA. The name it's marketed under is aspirin. And why do we do that? Well, because the molecule name might be complicated, it might not be so catchy, and when you're a company and you want to sell things and you want to make them memorable, and you also might want to jump onto a marketing bandwagon, because if there's a similar compound which works a similar way but it's not as good as your one, then on the other hand people are all using it, then by naming yours similar to it, it shows people that this drug probably does the following, and you highlighted a painkiller as an example, and many of these things have a doll at the end probably to say they dull pain. I don't know, but that's the reason why we do this. And so you will find that there will be multiple versions of a drug on the market. They all contain, let's say, paracetamol, but they might be marketed under different trade names or have other coloured packaging or whatever. But the way to tell is you look at the medicine's information number. There'll be a special identifier on that packet that tells you what the molecule is that's in it, and it should also name the drug molecule. And actually there's no evidence that if you buy one packet of something versus someone else's packet of something, if it's got the same amount of the active molecule in it, it shouldn't actually matter whether you take theirs or someone else's. The only difference often is the price.
Are you happy, James? Oh, James is gone. Let's go to Anna from Sea Point. What's your question for Chris?
Hi, good morning. I wanted to ask the doctor, I recently had what's called, it's like a heart attack, a Takotsubo cardiomyopathy. And I want to know the difference between a proper heart attack and this, and also what I can do in the future to prevent this from reoccurring.
Hello, Anna. Well, a cardiomyopathy, the name or the word cardio means heart, and myopathy, myo is muscle, and pathy means something's gone wrong with it. And therefore, if you have a cardiomyopathy, you've got something wrong with the muscle that is in your heart. And the heart is a big bag of muscle. That's how it pumps. When you have a heart attack, this is quite a different phenomenon. A heart attack is the blood vessels, the coronary arteries, which wind their way around the surface of the heart and send blood into the heart muscle, because the heart's pumping all the time. It has a high demand for oxygen and sugar to keep it going. The arteries provide the blood flow that brings in the oxygen, brings in the sugar, and takes away the waste products. Over time, with age, and in certain people, these arteries can become obstructed or clogged by a process called atherosclerosis, which is the build-up of fatty deposits, including cholesterol, in the wall of the artery. This narrows the hole through which the blood can flow, restricting the flow of blood, and occasionally one of those blockages can rupture or break down, and it completely blocks the blood vessel. This starves the heart tissue downstream of its blood supply, and if this isn't unblocked quickly, then the heart muscle can die. That process is a heart attack, and the consequence of a heart attack can be that patch of muscle dies and is replaced by fibrous tissue, and that part of the heart doesn't function properly afterwards, which can lead to heart failure. Cardiomyopathy can also cause heart failure in the sense that it's an inability of the heart to pump hard enough, but they're actually two quite different phenomena, although their outcomes and the consequences for the health of the person can be quite similar.
You know, Chris, this question is important in the context of your initial story about the gene screen for heart disease. I mean, is this something that they could potentially foresee then?
As in cardiomyopathy, yes, because there are a number of these cardiomyopathies that are inherited, familial cardiomyopathies. We know some of the genes which are linked to them, and therefore you can make this part of a screening program. Also, if it's been diagnosed in one family member and you're known to have one of these disorders, then it's worth keeping an eye on offspring, because there's a higher than average chance that they may have inherited those genes and therefore may be at risk of developing the same problem. At the moment, though, there's a limit to what we can do about them, because they are caused by a variety of factors. Things go wrong with the heart muscle itself, and at the moment we can't genetically fix people. We can't go in and say, well, we'll just put that gene right in that part of the body. That's coming, and in the future we almost certainly will be able to do that, but at the moment we can't. There are also other causes for cardiomyopathy. Infection can do this. There are some viruses that seem to cause inflammation in the heart muscle and sometimes reversibly, sometimes permanently damage it. Also toxins. Alcohol. If people drink too much, it can cause alcoholic cardiomyopathy, and the heart becomes baggy, saggy, and bigger than it should be, probably because of some direct toxic effect of excess alcohol consumption over a long period of time.
Thank you, Chris. We go to Patrick in Khayelitsha. What's your question for Chris?
Yes, good morning, Khader.
Good morning.
Hi, the naked scientist.
Go on, Patrick. What do you want to know?
Go on. What's your question?
My question, Chris, is about Truvada. Truvada the HIV preventive drug? Truvada. What does Truvada do to the HIV virus? That is first question. The second question, what do antiretrovirals do to the virus? And third question, why can not the combination of the two be used to fight the virus once and for all?
Okay, Patrick, a lot of questions there. So most people are familiar with HIV, human immunodeficiency virus. This agent spreads in a variety of ways. It can be spread by sex and also in blood products. The virus has a tropism. It attacks white blood cells called CD4 lymphocytes. It gets into those white blood cells. It inserts a copy of the virus genetic information into the DNA of the cell, and then periodically, from that lurking genetic impression of the virus, it can come back, it can turn the cell into a virus factory, spill out thousands of new copies of the virus into the bloodstream, and go and find other white blood cells, and in the process, the immune system is compromised. Now, because these viruses are sufficiently different to the way our own human cells work, scientists have been able to find ways to make molecules that can get in the way of some of those steps in the virus life cycle. The drug Truvada that you mentioned is actually a combination of two agents. One's called emtricitabine and, what was the other one? Emtricitabine and tenofovir. That's it. It's the other agent is called tenofovir. And these two things target the virus from two different angles because it's got to get into the cell, it's got to copy its own genetic material into a format that can be compatible with being inserted into the DNA. That's where Truvada intervenes. And then it's got to come back out of the DNA, make a new virus particle and spread around the body. So what these drugs do, including Truvada, is they are targeting some of these steps that are unique to the virus and are not found naturally in your healthy cells. So therefore you can make a drug which won't have high levels of side effects. It won't damage your normal functioning of your cells, but it will hit your the virus replication. And the idea is to suppress the virus so that it can't grow very well. And this is compatible with the best health. Does that answer your question?
Okay. I think Patrick's happy. Let's go to the one last question from Mavuso in Centurion. What's your question for Chris?
Good morning. I've seen a lot of documentaries on the different ways the Egyptian pyramids were built. And up to now, I do not have any one single conclusive answer as to how these pyramids were actually built, considering those huge blocks of rocks to those heights at that level of technology for that period of the Egyptian the pyramids when they were being built. The second thing is the theory about giant human beings being able to pick those rocks up. Does the professor have a conclusive one method how the Egyptian pyramids were actually built? Thank you.
Yeah, they're an amazing phenomenon, aren't they? And they've lasted like a time capsule, shining a light back 5,000 years or so, which is when they were being constructed. The answer is that they are blood, sweat and tears went into those pyramids. They took decades to centuries to complete. Many of them were started before the occupants were even born. And that's because, as you allude to, the amount of work involved to move blocks that weigh enormous amounts is absolutely huge. But what the Egyptians did leave behind is writing, and we have a lot of writings from the ancient Egyptians about what they thought about health, what they thought about disease, what they thought about daily life, and we can read that because people can decode hieroglyphs. And we know who built the pyramids, we know how they were built and for whom and why they were constructed. We know that people had fairly primitive instruments with which to quarry stone. They knew about rolling stone on rollers and with big ropes and teams of people to pull them along. And so that endeavour did lead to the pyramids. They also had an idea of how to get angles right and alignments. They also knew that water would find its lowest level. So one way that you could make sure things were straight was by having a long column of water. If you have effectively a groove cut into a bunch of stones and you put water in, you can measure the level of the water at one end and the other. And if the stone is flat and level, then the water will be the same height all the way along. wrong, for instance. So they had these primitive tools and they had a lot of time, and they also practiced a lot, and mistakes were costly. So they tried not to make them, because probably if you did make a mistake and you were the chief engineer, you probably would have your head chopped off if you got it wrong. So there was a pretty strong incentive to get it right.
Thank you, Christian. I've often wondered if there isn't a movie about the making of the pyramids, actually, now that we...
I think there is. There are definitely no giant humans involved. There were giant humans. People about 300,000 years ago, our human ancestors were very, very large indeed. And there are specimens of them in the Origin Centre and at the University of Witwatersrand that you can go and see. And yes, they would have made some of our modern basketball players who are tall today look relatively modestly sized. And that period lasted a while. There were big people around, but anatomically modern humans like us, well, we've been scrawny for 60, 70,000 years or so. And certainly the guys who built the pyramids were very similar to the modern human you see today.
Yeah. Thank you very much, Chris, for joining us.
You're
today.
welcome.
Your answers are very interesting and informative. Thank you very much.